All right, here we are in our last section of chapter 8. So you probably did the warm-up. It should be pretty straightforward. So you're finding a 99% confidence interval for the true mean. So one sample t-interval for means. Random, it was stated. Normal, it was stated if you didn't pay attention to that. Normally distributed. Independent, so it's a sample without replacement. So we're going to check our 10%. Check there. The formula, so I found the negative side again. I rounded it to 3 decimal places, so that 8 rounds up that 9, which rounds up to 4. That would be my t-star. If you use the calculator, again, pretty much the same answers. Captures the true mean maximum heart rate. So if I were doing the 95% instead of the 99, I would have a narrower interval because my critical value is going from 3.25 to 2.262. Just think about it. So what we just did up here was the 99. So to capture 99% of the area, you have to be pretty far out. So those critical values, so this is like your negative t-star and your positive one over here, have to be kind of far out. If I'm doing 95, I don't want to capture as much area in the middle, so I don't go as far out. So those numbers aren't quite as far away, so therefore what I'm adding or subtracting in my margin of error is now smaller. Okay? All right, so what we didn't really talk about yesterday is that what happens if that normal condition is not met. So fortunately for us, the T procedures are considered robust. So the robust just means that the probability calculations remain fairly accurate if a condition is violated. And in this case, the condition that we're speaking of is that normal condition. So if your simple random sample is less than 15, so your sample size is less than 15, you could use the T procedures if data appear close to normal. So you want no skew or outliers. If you're at least 15 but less than 30, you're okay as long as there's no outliers or strong skew. So in both of these cases, you don't want outliers. Here you can handle some skew. Here you really don't want any skew at all. If you're at least 30, you're fine because of the central limit theorem. So if you look at these examples down here, determine whether we can safely use a one sample t interval to estimate the population mean in each of the following settings. So to estimate the average GPA of students at your school, you randomly select 50 students from the classes you take. Here's a histogram of their GPAs. So now when you look at this one right here, so you know that it's 50 students. It's like, okay, that's great. So I don't really care what the graph looks like because according to my central limit theorem, if my sample size is greater than or equal to 30, then that normal condition has been met. So but the problem with this one is that it's not the normal check that's actually a problem. It's not truly that you did take a random sample, but the problem is that it's not a random sample representative of what you're interested in. You're interested in estimating the average GPA of the students at your school, but you only took them from students at the classes you take. So here you are sitting in an AP class. So if you're taking a bunch of AP or accelerated classes, and you try to estimate the average GPA from just that group of kids, you're clearly not going to get a very representative sample. It's a sample of just the kids that you are in class with, but it's not a sample. It's not going to achieve your goal here. So that's why I would not use a one sample t interval. So the normal check is fine. It's the other check. It's not a representative sample. And this usually, I rarely give you a problem where this is an issue. All right, so next one, the dot plot shows the amount of time it took to order and receive a regular coffee in five randomly selected visits. So you have a sample size of 5, so you're less than that 15 there. So we don't want any skew or outliers. So here we are with a little outlier there, so we have an issue here, okay? Last one, the box plot shows the SAT math score for a random sample of 20 students. So I've got 20, so I'm in that middle range there at your high school. I see a little bit of skew here, but again, no outliers. The skew's not strong. It's not a tiny sample. So I'm going to say I'm okay here. Moderate skew, I'm okay to proceed. Okay? All right, so basically, if you don't know your sample size, you are going to have to look at a graph. So we did this back in chapter 2. Remember we talked about assessing normality. And one of the things that we did is we looked at a histogram and we looked at a box plot, or we looked at a dot plot, or we looked at the normal probability plot. So any of these things you could look at to kind of figure out, is my data normal or not. We could also look at a stem and leaf plot. I'm going to focus on the histogram, box plot, and the normal probability plot because those are the ones that the calculator can do for me, okay? All right, so this next one right here. So as part of their final project, Christina and Rachel randomly selected 18 rolls of generic brand toilet paper to measure how well the brand could absorb water. They pour a quarter cup of water into a hard surface and counted how many squares it took to completely absorb the water. So here's the results from their 18 rolls. And I didn't type these in ahead of time, so I'm typing them in very quickly right now. Okay. All right, so just like before, I want to calculate a 99% confidence interval for the true mean. We're doing a one sample t interval for means. Random, so yes, they randomly selected 18 rolls. All right, for the normal check, the problem, obviously always check, does your problem tell you it's normal? If the problem tells you it's normal, don't go through the process of like making me a graph. Read the problem. So if it says it's normal, you're good. So it doesn't say it's normal here. The next thing you want to check is the sample size. So if the sample size is greater than or equal to 30, if you're talking about means, the central limit theorem applies. So here I have 18, so not 30. Okay, so problem doesn't say it's normal. I don't have a sample bigger than 30, so therefore I'm going to have to look at a graph. So again, here you have choices. So if I have all these data typed in here, and I just want to check to make sure I typed them in correctly. So let me just check something real quick here. Yes, my numbers are matching up, so I'm good. Okay, so you have choices here with your graphs. I have a couple things here, my y equals, so I'm going to get rid of those. All right, so with my graphs, you could look at a histogram. Whoops. So I typed all my data in list 1. Pick whatever color you like. Remember, we always do zoom 9. We did change the X scale before if you still want to change that to a whole number. So remember, we go to window. It's the distance between the tick marks and the axis. So we always rounded it up, but then we'd hit graph. So if you wanted to do that, that's fine. All right. The key thing to note here, this is the sample. This is not the population. I just want to know, is there anything that concerns me about the sample that makes me think my population might not be normal? So if I look at this picture right here of my sample data right now, I don't really see anything alarming. There's no skew, I don't have any outliers, so at this point there's nothing here that suggests to me that the population might not be normal. If you don't want to look at the histogram, look at the box plot. Make sure you pick the one with the outliers. I like to change the colors. Again, nothing here that makes me think my original population might not be normal. Last thing you can do, look at that normal probability plot. Again, do that zoom 9. There's a little bit of a tick here, but it's only a couple data points, so I'm not overly concerned here. But again, nothing here in this normal probability plot, remember we're looking for a straight line, that suggests to me that this data might not be normal, or that the population data. Again, the sample data, this is just a sample, it's a small representation of my larger population. I'm trying to figure out, do I think the population could be normally distributed or not? All right, so pick a graph, whatever one you want, and you're going to draw me a sketch of it and comment on it. So if I go back here and I use the histogram. If you want to use the box plot, that's fine. So I just put a little sketch there. Give me the sketch. I'll take off if you don't. And the histogram shows no outliers or major skew. So then sketch, comment. They took a sample here, so I'm going to check my 10%. So I know, I'm not assuming, I know that there's at least 180 rolls of toilet paper out there in the world. All right. To do this on the calculator, you either have to, if you want to use the formula, you're going to have to go to StatCalc, one of our stats, and you're going to have to get your summary stats. And then you'd have to find your t-star for the 99% with the 17 degrees of freedom. You can also use, so I'm going down to 8. This is a t distribution. It's a t because I don't have the population standard deviation. I'm going to have to use the standard deviation for the sample. If you notice here, it actually populated all those values in there. The only reason why it did that is because I just ran that one var stats. If you don't run the one var stats first, it doesn't have it there. That's fine. Just go over the data option. My data is in list 1. My confidence level, so in this one I'm doing a 99. Leave the frequency as 1. I press enter. If you're using the data option, give me your outputs. You can add the degrees of freedom. Give me the interval. And then the conclusion looks the same as it always looks. Okay, so we are 99% confident that the interval from blank to blank captures the true mean number of squares of toilet paper used to absorb a 1/4 cup of water. Okay. All right. The other thing that falls into this chapter is this idea here of these matched pairs. So a matched pair, well, so here's an example. So we have a study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are given in the table below. The values are before and after hypnotism. The measurements are in centimeters on a pain scale. So the first question asks you, why is this a matched pair? So this would be considered a matched pair because you have, each participant is matched with himself. You have 2 measurements on each person. So, and those 2 measurements are coming from the same person, so each measurement, they're like dependent on each other. So like matched pairs is also sometimes called dependent samples, so you have like a dependent scenario, okay? What I'm going to do here is I'm going to type all these values into the calculator, but remember, these are matched, so you can't like switch up the order of these. That 9 has to stick with that 7.4, that 8.1 sticks with that 6.1. All right, so these are all matched together. I come over in list 3, and that's where I'm going to do my difference. So I want to find the 99% confidence interval for the true mean difference. It's a 1 sample t-interval for means. If you notice here, I put the matched pair in there. Random, so it's stated here that they are randomly selected subjects. All right, the normal check. All right, so what I need to do here is I need to check a normal check of the differences. I don't want to check each one separately. I'm doing an analysis here on the differences. So if you notice here, I'm over here in that list 3. I'm going to go up. So I use the up arrow, black box. I'm going to press enter. So the black box, cursor blinking. And I'm going to do after minus before. You don't have to do it that way. That's just how I'm doing it, okay? Because if I do after minus before, if their pain has reduced, then this is going to, if I do after minus before, I'll end up with more negatives, okay? So here's my differences. When I look at the graph, I'm now looking at that list 3 there because I want to look at the graph of the differences. I'm not looking at L1 and L2 separately. I'm looking at the differences. So if you look at that graph, if you want to change this, I don't know, these already have 1 decimal place, so maybe I'll leave 1 decimal place there. So I look at the graph. That 1 bar got a little bit off the screen, so there's 3. Again, I'm not looking for this to look normal, but I'm just looking at this and saying, oh, is it possible that this came from a normal distribution? Is there anything here that alarms me or concerns me? It makes me think it might have not come from a normal distribution. You can also look at our normal box plot. So again, looking at the box plot there of that list 3. And of course, again, you can look at that normal probability plot. And you know I'm going to change the color again because I just like to look at all these colors. That one looks a little wonky. Probably not going to stick with that one. Just for the sake of being different on this one, I actually referenced the box plot. What other color? Ooh, yellow. I don't think I like yellow that much. Nope, it's kind of hard to see. Let's fix that. I don't like that color. white. That'll be impossible to see. Grays are not fun. Let's go back to pink. All right, so again, just like before. So my sample size is less than or equal to 15. So I'm going to look at the graph. I just draw my sketch there, and I comment on it. It shows no skew or outliers, okay? Independent, I'm going to assume at least 80 people using hypnotism for pain relief. Okay, again, same thing here. When I go to stat tests and I do that t-interval, I am using the data option. You can use the stat option, but if you notice here, I didn't run that 1var stats yet on that list 3, so nothing's populated here. If I go there and I do the 1var stats of list 3, and now I went to that stat test 8, voila, all those things get populated. But we'll just use the data option again. We're going with list 3. I am doing a 99 again here. Hit calculate. So again, those are my outputs. Give me the degrees of freedom. There's my interval. So you're 99% confident that the interval from negative 3.822 to 0.7203 captures the true mean difference after minus before. Okay, this is important here. Somewhere in this problem, you need to tell me which direction you did your difference, because you could have done before minus after. Okay, if you did before minus after, let's just look here. So the before is in list 1. So if I did before, oops, I'm having trouble with my keys today. If you notice here, the sign switched. So what's going to happen here when I do my interval? Okay, look. So this number is over here, but it's negative. This number is over here and it's positive, right? So that just had that flipping there going on. But again, somewhere you need to tell me what way you did it so I know, okay? So if you don't want to tell me here, tell me back up toward the top, but somewhere you got to tell me. So here's my question to you. Can we say that hypnotism reduces pain? So no. 0 is in the interval. So 0 is a possible value. 0 is in that interval, which means there may be no difference on average. Again, this is on average. Some people it did get better, some people didn't get better, but on average, 0 is in that interval. So on average, I'm saying there's not an improvement, okay? All right, same thing here. You've got SAT scores. Again, we've got this matched pair scenario because we've got kids that are taking it before and after. Again, we've taught, you can pause the video and go ahead and go through this, but you know, you've got all your steps there. Again, I looked at a box plot of the differences. I made my assumption there. Again, give me those degrees of freedom. And then did the SAT class improve scores? Again, it's possible there's no improvement on average. Again, I'm talking about on average since 0 is included in the interval. So for your typical kid, there was no improvement, okay? I think, I don't know if those are the problems or not. Let me look here. No, yes. Yeah, the problems, they're just in a different order. There they are. How fun. All right, that is that for this section here.